Download this code from codegive.com, link in the description below. OK, let's dive into the world of logic, starting with its foundational concepts and then progressing to strong normalization with a code example. Part 1, Foundations of Logic. Logic is the study of reasoning. It provides a formal system for evaluating arguments and determining whether they are valid, i.e., whether the conclusions follow necessarily from the premises. It's essential for mathematics, computer science, philosophy, and many other fields. 1.1 Basic Concepts. Asterisk proposition, statement, a declarative sentence that is either true or false, but not both. Examples. Asterisk, the sky is blue. True. Asterisk, 2 + 2 = 5. False. Asterisk, it is raining. True or false, depending on the context. Asterisk, what time is it? Not a proposition, as it's a question. Asterisk, truth value. Asterisk, the truth or falsity of a proposition. Represented as true, T, or false, F. Asterisk, logical connectives, operators, symbols used to combine propositions into more complex propositions. Common connectives include asterisk, negation, or not P. The negation of a proposition is true if the proposition is false, and vice versa. Asterisk, conjunction, or and P and Q. The conjunction of two propositions is true if and only if both propositions are true. Asterisk, disjunction, or P or Q. The disjunction of two propositions is true if at least one of the propositions is true, inclusive or. Asterisk, implication, rightward arrow or proper superset symbol. If P, then Q. Also read as P implies Q. The implication is false only when P is true and Q is false. It's true in all other cases. This can be a point of confusion, so remember its truth table. Asterisk, biconditional, left-right arrow or P if and only if Q. The biconditional is true if P and Q have the same truth value, both true or both false. Asterisk, truth table. Asterisk, a table that shows the truth value of a compound proposition for all possible combinations of truth values of its constituent propositions. Truth tables for common connectives. PQP, PQ, PQP, rightward arrow, QP, left right arrow, Q. Dash, 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 dash. True, true, false, true, 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 true. True, false, 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 true, false, false. False, true, true, false, true, true, false. False, false, true, false, false, true, true. 1.2 Propositional logic, syntax and semantics. Asterisk, syntax. Asterisk defines the rules for constructing well-formed formulas, WFFS, in propositional logic. Typically, it includes asterisk, propositional variables, example P, Q, R. Asterisk, logical connectives, rightward arrow, left right arrow. Asterisk, parentheses, to group expressions. A typical syntax definition is asterisk, a propositional variable is a WFF. Asterisk, if A is a WFF, then A is a WFF. Asterisk, if A and B are WFFs, then AB, AB, a rightward arrow B, and a left right arrow B, are WFFs. Asterisk, nothing else is a WFF. Asterisk, semantics. Asterisk assigns meaning to the WFFs. This is done through truth assignments, where each propositional variable is assigned a truth value, true or false. The truth value of a compound WFF is then determined by the truth tables of the logical connectives. Asterisk, interpretation. Asterisk, a mapping from propositional variables to truth values. Asterisk, model. Asterisk, an interpretation that makes a WFF true. If an interpretation I makes a formula A true, we say I is a model of A, written I equals A. Asterisk satisfiable asterisk a WFF is satisfiable if there exists an interpretation that makes it true, i.e., it has a model. Asterisk unsatisfiable, contradictory a WFF is unsatisfiable if there is no interpretation that makes it true. It is always false. Example, pp. Asterisk tautology, valid a WFF is a tautology if it is true in all interpretations. It is always true. Example, pp. Asterisk logical equivalence asterisk 2 WFFs A and B are logically equivalent, written AB, if they have the same truth value in all interpretations. This means their truth tables are identical. 1.3 Inference rules and proofs. Asterisk inference rule asterisk a rule that allows us to derive new WFFs from existing WFFs. A common way of representing an inference rule is asterisk modus ponens asterisk a fundamental inference rule. If we know that P implies Q is true and we know that P is true, then we can infer that Q is true. Asterisk modus tollens asterisk another important rule. If we know that P implies Q is true and we know that Q is false, then we can infer that P is false. Asterisk hypothetical syllogism asterisk. Asterisk proof asterisk a sequence of WFFs, where each WFF is either an axiom, a predefined true statement, a premise, an assumption, or derived from previous WFFs in the sequence using inference rules. The last WFF in the sequence is the conclusion. Asterisk soundness asterisk a logical system is sound if every provable statement is also true. In other words, the inference rules only lead to correct conclusions. Asterisk completeness asterisk a logical system is complete if every true statement is provable. Part 2, Lambda calculus and reduction. To understand strong normalization, we need to first grasp the basics of the lambda calculus. 2.1 Untyped lambda calculus. The lambda calculus is a formal system for expressing computation based on function abstraction and application. It's a universal model of computation, meaning it can express any computation that can be expressed by a Turing machine. Asterisk syntax asterisk the lambda calculus has a very simple syntax. Asterisk variable asterisk x, y, z, etc. Asterisk abstraction asterisk lambda x. M, where x is a variable and m is a lambda term. This represents a function that takes an argument x and returns m. Asterisk application asterisk, mn, where m and n are lambda terms. This represents applying the function m to the argument n. Asterisk free and bound variables asterisk. Asterisk in the term lambda x. M, the variable x is bound within the scope of the lambda abstraction. Asterisk a variable that is not bound is free. Asterisk example, in lambda x. X y, x is bound, and y is free. In lambda x, y, x is bound within the abstraction, and y is free. Asterisk substitution asterisk the process of replacing a free variable with a term. We write mx equals n to indicate substituting n for all free occurrences of x in m. Substitution needs to be done carefully to avoid variable capture. Asterisk alpha conversion renaming bound variables. Lambda x. M is equivalent to lambda y. Mx equals y if y is not free in M. This is important for avoiding name clashes during substitution. Asterisk example, lambda x. Xy is alpha equivalent to lambda z. Zy. Asterisk beta reduction the fundamental reduction rule in the lambda calculus. It represents function application. Asterisk, lambda x. m, and rightward arrow mx equals n. Asterisk this means applying the function, lambda x m, to the argument n involves substituting n for all free occurrences of x in m. Asterisk eta conversion, eta conversion if x is not free in m, then lambda x mx rightward arrow m. This captures the notion of extensional equality. If two functions produce the same result for all inputs, they are considered equal. 2.2 Reduction strategies. When a lambda term contains multiple redexes, reducible expressions, the order in which we perform beta reduction can matter. Different reduction strategies define the order. Asterisk normal order reduction asterisk always reduce the leftmost, outermost redex first. This strategy is guaranteed to find a normal form if one exists. It's sometimes called lazy evaluation. Asterisk applicative order reduction asterisk always reduce the leftmost, innermost redex first, but only if the redex is already a value, i.e., a variable or a lambda abstraction. This corresponds to eager evaluation or call by value. Asterisk call by name asterisk substitute the argument directly into the function body without evaluating it first. This is similar to normal order, but it may evaluate the same argument multiple times. Asterisk call by value asterisk evaluate the argument before substituting it into the function body. This is similar to applicative order. 2.3 Normal forms. Asterisk normal form asterisk a lambda term is in normal form if it contains no redexes, i.e., no beta reductions can be performed. Asterisk weak head normal form, WHNF a term that is either asterisk a variable, asterisk a lambda abstraction, lambda x m, asterisk an application of a variable to another term, xm. WHNF is a weaker condition than normal form. A term in normal form is also in WHNF, but the reverse is not necessarily true. WHNF is important in practical functional programming languages because it allows us to stop evaluation at a certain point and still have a meaningful result. Part 3, Normalization and Strong Normalization. Now we get to the key concepts. 3.1 Normalization. Asterisk normalization asterisk a lambda term normalizes if there exists a sequence of beta reductions that leads to a normal form. In other words, if you can keep applying beta reduction until you reach a term that cannot be reduced any further, then the original term normalizes. Asterisk weak normalization asterisk a lambda term has a weak normal form if there exists a reduction sequence that leads to a term in WHNF. 3.2 Strong normalization. Asterisk strong normalization asterisk a lambda term has the strong normalization property if every possible sequence of beta reductions eventually terminates in a normal form. This is a very strong property. No matter how you choose to reduce the term, you will always end up with the same normal form, and you will eventually reach it. Key differences summarized. Feature normalization strong normalization. Definition at least one reduction sequence reaches NF. Every reduction sequence reaches NF. Reduction order one specific order is sufficient. Order of reduction doesn't matter. Termination may not terminate for all reduction orders. Always terminates, regardless of the reduction order. Guarantee of result no guarantee of uniqueness of the NF. Guarantees a unique normal form. Important considerations asterisk. Asterisk untyped lambda calculus asterisk the untyped lambda calculus is not strongly normalizing. There are terms for which some reduction sequences terminate in a normal form, while other sequences loop forever. A classic example is the omega combinator, lambda xxx, lambda xxx. Reducing this term always leads back to itself, Creating an infinite loop. Typed lambda calculus. Typed lambda calculi. Example: the simply typed lambda calculus can be strongly normalizing. The type system restricts the kinds of terms that can be formed, which can prevent infinite loops and ensure that all reduction sequences terminate. Strong normalization is a desirable property for type systems because it ensures that programs will always terminate. 3.3 Example in untyped lambda calculus, illustrating non-strong normalization. 1 omega rightward arrow, lambda xxx, lambda xxx, it reduces to itself. 2 omega rightward arrow omega. 3 omega rightward arrow omega. 4. This goes on forever, it doesn't terminate. In contrast, consider the term reduction 1, lambda xy, omega rightward arrow y, this terminates in a normal form y. Reduction 2, lambda xy, omega rightward arrow, lambda xy, omega, rightward arrow, lambda xy, omega, rightward arrow, goes on forever if we keep reducing the omega part. Since there exists at least one reduction sequence that leads to a normal form, y, the term, lambda xy, omega normalizes. However, not all reduction sequences terminate, so it's not strongly normalizing. Part 4, Strong Normalization and Type Systems, with code example. The key to achieving strong normalization is often through the use of type systems. We'll explore the simply typed lambda calculus and how it enforces strong normalization. 4.1 Simply typed lambda calculus. Types. The simply typed lambda calculus introduces types to the lambda calculus. Types are assigned to terms to classify them and restrict their usage. Commonly, we have base types, atomic types like int, bool, etc. Function types, t1-t2, which represents a function that takes an argument of type t1 and returns a value of type t2. Typing rules, rules that govern how types are assigned to terms. Some basic rules include variable if variable x has type t in the context gamma, then gamma x, t. Abstraction if, assuming x has type t1, term m has type t2, then gamma, lambda x, t1. M, t1-t2. Application if m has type t1-t2 and n has type t1, then gamma, mn, t2. Type context, gamma a set of type assignments to variables. For example, gamma equals x, int, y, bool means that x has type int and y has type bool. 4.2 Code example, Haskell. Here's a Haskell code example illustrating the concept of types and how they can prevent infinite loops. While Haskell's type system is much more sophisticated than the simply typed lambda calculus, it demonstrates the principle. In this example, type check function takes a type environment and a term, and tries to infer its type. If the term is well typed according to the typing rules, it returns just type, otherwise nothing. This kind of type checking, especially in a more sophisticated type system, can prevent the creation of terms that would lead to infinite loops during reduction. 4.3 Why types help with strong normalization. 1. Restricting recursive definitions. In the untyped lambda calculus, you can define functions that call themselves without any restrictions, like the omega combinator. Typed lambda calculi often restrict how recursive definitions can be formed, preventing infinite loops. 2. Ensuring function application is well defined. Types ensure that you only apply functions to arguments of the correct type. This prevents situations where a function might try to operate on data it's not designed for, potentially leading to an infinite loop. 4.4 Hindley-Milner type system. It's also important to note that some type systems, such as the Hindley-Milner type system, used in Haskell and ML, while being very powerful and providing type inference, do not guarantee strong normalization. They allow for recursion and general loops which can cause non-termination. Part 5, Summary and Key Takeaways. Asterisk logic is foundational. Asterisk understanding propositional and predicate logic provides a formal framework for reasoning. Asterisk lambda calculus is a model of computation. Asterisk it provides a powerful and simple way to express computation based on function abstraction and application. Asterisk normalization versus strong normalization. Asterisk normalization means at least one reduction sequence terminates, while strong normalization means all reduction sequences terminate. Asterisk typed lambda calculus can enforce strong normalization. Asterisk by restricting the formation of terms, type systems can prevent infinite loops and ensure termination. Asterisk strong normalization has practical benefits. Asterisk it guarantees that programs will always terminate, which is desirable for safety and predictability. I hope this comprehensive explanation helps. Let me know if you have any further questions.